So, after learning about Norton's dome on YouTube, I hastily made a video response to shed light on where the logic appeared to go wrong, thinking it would be sufficient to explain the loophole. Boy, was I wrong. Not about the dome being unphysical, but my explanation was a bit lacking. So now I hope to clarify my stance as it pertains to Norton's argument. The debate goes like this. When calculating the trajectory of the mass starting at the apex of the dome, there are two solutions. One allows the mass to stay put, the other allows the mass to slide down the dome. But since there is no apparent cause for it to roll down, Norton concludes that it can start spontaneously at some time t equals t. So he uses both solutions. All of us thinking folks say, well, that's ridiculous, nothing physical caused it to move, and we point to Newton's first law. Norton replies, but the first law requires that change from rest to motion can only be caused by a force, and there is a force in the interval where the motion begins, so the law is already satisfied. And so one looks a little deeper, as I did, and you see a discontinuity in the fourth derivative, called snap, where it goes from 0 to 1/6 at the time t equals t. And we say, see? Nothing causes this to happen, so it is unphysical. And Norton says, so what? Newton's laws are already satisfied, and spontaneity is a, quote, physical explanation for it. I see no problem. It's allowed to be discontinuous in the fourth derivative. And then there were papers written and a large discussion. Is it really Newtonian? Is it improperly idealized? Or is it one interpretation while we just prefer another interpretation? Norton says fine, but mine is the right one, the true one. And yet, we all know intuitively something is fishy. We want to discard the second solution, but Norton says we need a reason, and the reason cannot be because we expect determinism. Determinism is not an assumption. Why would there be two solutions if one is never used? Well, it turns out there is a reason to discard one, hiding in plain sight. An invisible barrier, if you will. The shape of the dome is such that the mass only experiences a net force when it is on an angled portion of the dome, anywhere but the apex. This gives a relation of force to spatial distance. But our solution is based in time. We're waiting for time t equals t to occur so that the force begins to exist. If you're not moving and just waiting, will you ever get to another destination? No, of course not. Because time and space are orthogonal, and they always will be, so it doesn't matter how long you wait, you will never get to r greater than 0. It's not Newton's axioms that keep it from moving off the apex, it's just simple geometry. But then the reaction is still, if you can't access that, then why is it a solution? Why does that second solution even exist? And the answer is that while it doesn't apply in this case, there are other cases with the same math, the same initial conditions, where it does apply. Let's say instead of a dome, we have a table. The mass can slide along the table, but only if we tilt it. The force is related to the angle, same as the dome. We just have to be careful to tilt it with the correct relationship to match Norton's solution, but we certainly can do that. Unlike the dome, though, we can start to tilt the table whenever we want. And as long as we tilt it in time according to the equation of motion, then the motion of the mass will be exactly the same as the second solution. So the force has a relationship with time instead of space. It's not orthogonal. So then we can accept that solution. And this also gives physical meaning for t. T is the time we start tilting the table. It's not spontaneous, it's not ambiguous. Norton's interpretation, on the other hand, can't tell the difference between those two scenarios. They are either both stationary or both spontaneous. So what's the moral of the story? Don't make reaction videos until you've got the answer right. No. Well, the moral is we have to interpret the math in the context of the physical scenario, that is, all of our assumptions. The math itself is completely agnostic in regards to the cause of forces. We assume gravity, we assume a spring exists, we assume rocket engines exist, but we must analyze if the force is applied orthogonal to time or not. Rockets provide thrust as a function of time, but springs provide force as a function of space. Most of the time in physics, we only get one solution, or the initial conditions rule out any problematic situations, so we don't have to check. But Norton managed to find this clever case where we do have to check. Norton didn't check and instead assumed spontaneity would resolve the ambiguity caused by the infinite curvature of the dome. But it doesn't. As Newton says, force is required to cause motion, but the force on the dome is only accessible in space, not in time. The mass will never move because no matter how long you wait, the force is never impressed thereon by anything. So, whenever you get two solutions in physics, you should always be thinking, what are these solutions for? What do they mean? If you don't ask that, then you're not doing physics, you're just doing math. And if you're doing philosophy, then you ask, why do we ask that? Which is what thought experiments like this are for. So kudos to Norton for bringing this up. It made us all think. And some people may still agree that Norton's interpretation of Newton's laws is correct, and that it leaves space for indeterminism. But if that is true, then it is just another problem that limits Newtonian mechanics, and a good reason to use a better theory.